My dear students, in this lecture I will discuss the X-ray diffraction technique. So it is a part of your BTech chemistry syllabus and I am Dr. Abhijit Shah. I will explain this X-ray diffraction technique to you. This unit actually comes in under Unit 5 in solid state chemistry. So in this unit we will discuss uh, about the solid materials, different type of crystals of solid materials. Now in crystal there are crystal plane, so we'll discuss what are the crystal planes, how we can determine crystal planes. We'll discuss about Miller indices, Weiss indices. We'll discuss Bragg law of X-ray diffraction and its derivation. So these are the points we'll discuss in this lecture. So in a matter can has different type of state: solid state, liquid state, gaseous state and plasma state. In gaseous state and plasma state, this matter has no particular shape, no particular volume. In liquid state, it has uh, volume, but it do not have specific shape. But in solid state, it has fixed volume and fixed shape. In this lecture, we'll discuss on this solid state of matter. So what is solid? Solid means it will have definite shape, definite volume. It will be highly incompressible. It will be rigid, and it has particles or molecules or atoms or ions which are present in that solid. They will be closely connected with each other by a strong intermolecular force, and the position of those constituent will be fixed. Now type of solid, there are two type of solid. One is crystalline solid, another one amorphous solid. Next, characteristics of crystalline solid. So the first characteristics of crystalline solid is the existence of crystalline lattice. A crystalline lattice is a solid figure which has a definite geometrical shape. Definite geometrical shape means you can see there are different definite geometrical shape. It will have flat face and sharp edges. Solid material, it will be incompressible. It will have definite melting point. It will have definite geometry. It will be diffracted by X-ray beam. Okay, the example: sodium chloride crystal, cesium chloride crystal, diamond. These are the some example of crystalline solid material. So in solid material, all the atoms are attached through strong intermolecular force, and this three-dimensional network of solid material, uh, or means the building unit which are of solid material, they are connected with each other by strong intermolecular force, and that force is long range ordered force. Means if the solid material size is big, still it is solid. Means this intermolecular force is not short range, it is long range. So long range intermolecular force is present in the solid material. In amorphous, the intermolecular force is very absence of long range intermolecular force. So it has no regular shape. It has haphazard arrangement of atom. Why it is haphazard? Because intermolecular force is less. It is non-crystalline. It has no specific or definite melting point. It start melted at some particular point, and that melting point change during melting. Let's say start melting, let's say 150 degrees Celsius, and it completely melted, let's say 155 degrees Celsius. So this 5 degree is the changing this melting point. It has no definite geometrical shape. Crystalline solid have definite geometrical, like cubic, like hexagonal, like circle or like whatever, some definite geometrical shape, but amorphous material has no definite geometrical shape. It will not diffract the X-ray. X-ray diffraction will be very weak. If you see X-ray diffraction of crystalline solid, you will get sharp lines, but in amorphous, we'll get some. There is no sharp line. Example: glass, rubber, plastic. The example of amorphous solid. Next. Now we'll discuss the crystalline solids, crystalline material. So in crystalline material, there is a part which is called crystal lattice or units and unit cell. What is crystal lattice? Say crystalline material, there is a definite arrangement of the atoms. So this is the one atom, is another atom, and there is another atom. So there is a definite arrangement of the atom. So a regular three-dimensional arrangement of points in space is called crystal lattice. So this is called a crystal lattice. Okay, a crystalline solid has atoms, okay, and these atoms are arranged in a proper way. This arrangement of atoms is called crystal lattice. Now, unit cell is the small unit. Let's say this is the shaded area. So, the unit cell is the smallest portion of the crystal where these atoms are present. And this unit cell actually repeated. Right? Let's say it is the unit cell. Now, it is repeated all over the crystal. Right? So, unit cell is the smallest portion of the crystal lattice which uh, where this arrangement of atoms are arranged in a proper shape. Now, when multiple unit cells are attached with each other, then we are getting this big crystal. Now, each unit cell can be divided into three coordinates: x coordinate, y coordinate, and z coordinate. Now, the unit length along the x coordinate is indicated by A. The unit length along y coordinate is indicated by B, and the unit length along z coordinate is indicated by C. So what is ABC? ABC are the of unit length of the crystal along the x coordinate. Means a unit cell of a crystal can be divided into three coordinate x, y, z. Now the unit length or unit distance, some specific distance along x-axis is called A. That is called unit length. Some specific distance along y-axis is called B. That is called unit length along B-axis. Some specific distance on z-axis is called C. It is called unit length along z-axis. Now the angle between axis A and Y, axis X and Z, axis Y and Z is indicated by this alpha, beta, and gamma angle. Okay. Now different unit cell has different values of ABC, different values of alpha, beta, gamma. Right. Now, based on these values like A, B, C, and alpha, beta, gamma, we can have different type of crystal system: cubic crystal, tetragonal crystal, orthorhombic crystal, monoclinic crystal, triclinic crystal, trigonal crystal, hexagonal crystal. Right? So these are the different type of crystal. How it is? Why different type? Because the units, because of the variation of the A, B, C, and this alpha, beta, gamma. When A, B, and C both are same, and alpha, beta, gamma is also same and 90°, we will get cubic crystal. Right? When again A and B same but not equal to C, and alpha, beta, gamma is 90, it's a tetragonal crystal. Right? So in that we will get different type of crystal, but we will discuss on cubic crystal mainly. Now in crystal there is another thing that is called crystal plane. What is crystal plane? So say this is one unit cell. This unit cell is divided by three coordinates: x coordinate, y coordinate, and z coordinate. Now in the unit cell, we can see there are different phases. This is one phase, this is another phase, this is another phase, right? Now these phases are called crystal plane. These phases are called crystal plane. Crystal plane actually, not only these phases, we can have crystal plane uh, uh, if we say 3 points in a crystal, okay, let's say lattice plane is passing to 3 points. Let's say we can have 3 points in a crystal, okay, 1.1, 0.2, and let's say another point 3, third point. So if we join this 3 point, right, we'll get one plane, right? To get one line, we need 2 points. To get one plane, we need 3 points, right? So if we consider three imaginary point and if we join this point, we'll get one plane, right? So this plane is called crystal plane, which is present in the unit cell. It can be present on the surface of the unit cell or it can be present inside of the unit cell. I'll show you the image. Okay, but remember that when we have only one point, it is called center, right? When we have 2 points, if we join by a line, we'll get a straight line. Now, if there are 3 points, we'll get one plane, right? To get one plane, we need minimum 3 points. Okay, now this 3 point, we can make some plane, right? So for example, here if we say 3 points, it's a point 1, point 2, and point 3, we can say point 1, point 2, and point 3, we can say this is one plane. Right? Now this plane, how we can designate this plane? We can designate this plane by some name that is called Miller indices. Right? How to get these Miller indices? To get the Miller indices, first step is we have to identify the intercept on x, y, and z axis. Say this is this shaded pink color plane, right? Let's say this is one plane, right? So what will be the name of this plane? The name of this plane will be indicated by Miller indices, that is HKL, right? So how we will get the values of HKL? We can get the values of HKL. First, we have to identify the intercept on x, y, and z axis. Intercept. Say for this plane is intersecting x-axis at a distance. Now this plane is parallel to y-axis and this plane is also parallel to z-axis. So it will intersect the x-axis at a distance, y-axis at infinity distance, and z-axis also infinity distance, right? Next is we have to take the fraction, we have to take the reciprocal of the intercept. So if we take the reciprocal, so x-axis intercept is a, so 1 by a. Z-axis intercept is, okay, uh, x-axis it is a distance, y-axis infinity, z-axis infinity. So if we take the reciprocal of x, y, z, if we have to take the reciprocal, if we take the reciprocal of unit distance a, right? So a by a, infinity by a, infinity by a. So we'll get 1 infinity infinity, right? So this plane cut x-axis at 1 unit distance a, y-axis infinity, and z-axis also infinity, right? So these are the reciprocal 1, infinity, and infinity, right? Now Miller indices will be we have to take the reciprocal. We have to take the reciprocal of the intercept. So reciprocal of 1 will be 1, reciprocal of infinity will be 0, and reciprocal then the infinity will be 0. So Miller indices will be 1, 0, 0. So this name of this plane will be 1, 0, 0 plane. Okay, let's take another example. Right. Okay. Let's say this is one plane. This is a green plane. If we talk about the green plane, what will be the Miller indices of the green plane? Now for this green plane, let's say it is intercept x-axis, right? X-axis is parallel to x-axis, so x-axis at infinity distance. It is parallel to y-axis also, so it will cut the y-axis at infinity distance, and it is parallel. It is cut the z-axis at unit distance a, right? So what will be the reciprocal? Reciprocal will be 1 by infinity, 1 by infinity, and 1 by 1, right? 1, 1. So reciprocal will be 0, 0, 1. So Miller indices will be 0, 0, 1. for this plane. Okay. Okay. Now what will be the Miller indices for this yellow plane? For yellow plane, now if we see the yellow plane, this one, yellow plane, if we see, it will cut the y-axis at a distance, right? It is parallel to x-axis and parallel to z-axis. So it will intercept of x-axis will be infinity, intercept of y-axis will be a, intercept of z-axis will be infinity, right? So again, if we take the reciprocal, we'll get 1 by infinity, right? 1 by infinity, 1 by 1, and 1 by infinity. So 1, 0, 1 will be the reciprocal. So plane will be 1, 0, 1, 0, right? The the yellow plane Miller indices will be 0, 1, 0. Okay, right? Okay. Now if we have some plane which cut x-axis as well as y-axis and parallel to z-axis, then what will be the Miller indices, right? Say first, so for example, this plane, right? So this plane cut x-axis at a distance, y-axis is also a distance, but it is parallel to z-axis. So intercept will be a infinity. So a infinity means if we take the reciprocal, we will get 1, 1 infinity. So Miller indices will be 1, 1, 0. Okay. So in that way, we can calculate the Miller indices. Another example, if say this plane, it is cutting x-axis at a distance, y-axis also a distance, and z-axis also a distance. So intercept will be a. So if we take the reciprocal, it will be 1 by, so a by a by a by a. So ultimately it will come as in 1, 1, 1, right? So in that way, we can calculate the Miller indices. So what in to calculate the Miller indices, we have to first find out the intercept. Okay, then we have to take the reciprocal, and then we have to get some integer. Okay, for example, for this plane, then let's say it is our unit distance a. This point is 1 by a by 2. This unit distance b. This unit distance c. Right. So for this plane is cutting x-axis at a distance, let's say 1 by 2. B a distance, let's say 1, and C at a distance, let's say 3 by 4. So if we take the reciprocal, 1 by 2 will be 2, B will be 1, and 3 by will be 4 by 3. Now if we have to make the integer, we have to multiply it by 3. So 3 into 2 6, 3 into 1 3, and 4 by 3 into 3 will be 4. So 6, 3, 4 will be the Miller indices for this plane. Okay, so in that way we can calculate Miller indices. So what we have understood till now, we have understood that uh, we have understood the characteristic of solid material. What is solid material? That solid material means it will have definite shape. It will be crystalline. If we perform X-ray diffraction, we will get sharp lines. Right? In solid material, there will be unit cell. This unit cell can be different type: cubic, tetragonal, triclinic, different type. Now, in cubic unit cell is our main focus. In cubic unit cell, we have seen that how to calculate the Miller indices. This Miller indices actually indicate the crystal plane. Crystal plane. So calculate the Miller indices. There are 3 steps. We have to take the, we have to find out the intercept. Then we have to take the reciprocal, and then only we will get the Miller indices value. Now, finally, we have to talk about the distance between distance between these crystal planes. Okay, to calculate the distance between crystal, we have one formula for cubic unit cell. Formula is HKL is the Miller indices value. This HKL value will be given, right? Now, if there is a value will be also given. Now, this is the formula: DHKL equal to a divided by root over h square plus k square plus l square. So using this formula, we can calculate the distance between these crystal planes. Okay. Now, if we calculate the distance, it will come to the as in come the value will come in a nanometer range. Since it is the nanometer range, so we can use X-ray radiation. So X-ray radiation actually have also the wavelength of X-ray light is also in the nanometer range. Because of that, we can use X-ray radiation to calculate the distance between crystal planes. This is the formula. Using this formula, we can calculate, and experimentally also we can calculate the distance between crystal plane using X-ray method. What is X-ray method? So this is the X-ray method. In X-ray method, we have to use the Bragg equation. So this is the Bragg equation. Bragg equation is n lambda is equal to 2d sine theta. So what is n lambda? N is a one integer. Okay, lambda is the wavelength of X-ray radiation. Sine theta, theta is the this angle, incident angle of the X-ray light on crystal plane. D is the distance between crystal planes. Okay, so using this formula, using this Bragg experiment, we can calculate. We can calculate the distance between crystal plane. We can calculate the distance between crystal plane by the formula as well as by the experiment also. So in this experiment, we have to take the crystal, we have to keep the crystal inside the instrument. Now crystal has some planes. Let this blue line indicate the planes. Let's say this is the HKL plane of the crystal. Let's say DHKL is the distance between the planes. Now when X-ray light is coming, so let's say first X-ray light is interacting with this first plane and reflected like this. Okay, not reflected, you can say scattered. Second X-ray light uh, interacting with the second plane and scattered in this way. These two lights, first ray and second, they are parallel line, they will be parallel. So when they are scattered or reflected, it will be also parallel. Theta is the angle between this crystal plane and incident X-ray radiation. Okay, so if this angle is theta, this two angle will be also theta. Okay, so O is the point where second X radiation interact with the second plane, and this point is the where first X radiation interact with this plane. Now these two, this line, these two ray, they are going to the detector. Now detector can detect these two rays and calculate the distance between the plane if these two radiation are in the same phase. Now, if these two radiation are in the same phase, then only detector can detect the scattered X-ray radiation. Because if two waves are in opposite phase, then uh, one wave, if two waves in the opposite phase, then there will be no constructive interference. If there is a destructive interference, the detector will not get any signal. So therefore, detector will get signal if two waves are in the same phase. If then only there will be constructive interference and detector will get the signal. Now, when these two waves will be in the same phase, if the excess path, so first X radiation, second X radiation. So second X radiation is entering into the crystal second plane and then it is reflected or scattered. So second X radiation is following some extra path. What is the extra path? This extra path is the AOB, is the extra path. That this extra path actually, and this second X radiation is travel this AOB extra path. Okay, now if this AOB extra path, if this extra path is equal to n lambda, this AOB, this extra path is equal to n lambda, then only this second wave and first wave will be in the same phase. Right? So what is the condition? Condition will be AOB, this extra path should be equal to n lambda. Now we have to calculate this AO and OB. Right? Now if we see this triangle, this another triangle, this AO, it will come as in d sine theta, right? This d sine theta, and OB will be also d sine theta. So AO and OB, it will be d sine theta plus d 2d sine theta. So in that way we'll get 2d sine theta will be equal to n lambda, right? So first we have to say this extra path traveled by the second ray must be equal to that n lambda. N is the integer 1, 2, 3, 4 like that. And now this extra part will be equal to d sine theta plus d sine 2d sine theta. In that we will get this formula. This 2n lambda will be 2d sine theta. Okay, so this is the picture of X-ray instrument. Inside the instrument we have to mount this crystal and then X-ray radiation will come and reflect it. Okay, so this is all about this XRD technique. And whatever in your syllabus we have discussed in this lecture, so you have to read the derivation of Bragg equation, that is n lambda equal to 2t sine theta. We have to also know to calculate the Miller indices. We have to know the calculation of the interplanar distance like DHKL value for cubic crystal using that formula, that is DHKL is equal to A divided by root over E square plus K square plus L square. Okay, so these are the all about this X-ray technique, X-ray diffraction technique. Okay, I hope you have understood. Thank you.